So it's our pleasure to present Empirical. He's currently assistant professor at Carnegie Mellon University in the machine learning department. He recently finished his PhD from Stanford, and you probably know his amazing work in the area of state space models that really rocked the field and even pushed people like Cesar Rash to claim that there is probably a successor to transformers. So the work that has been doing around state space models is super exciting, and it's really the first breath of fresh air that we had in this architecture landscape for a while. So I'm very excited to hear about his talk.
Thank you. Okay, looks like it's on. Yeah, thank you for the introduction. For this talk, I'll give an overview of the landscape of the field for this particular research area about state space models, which is something that has been fairly recent and developed over the last couple years. This is a work I did as a PhD student a couple years ago, as mentioned, at Stanford. And now I'm at Carnegie Mellon, just started last year, and continue to work on this. And I also, as was alluded to in the panel, I'm somebody with industry affiliations as well. I have a startup called Cartesia where we're applying these more on the application side. So these are things that are really practical and have a lot of nice properties and benefits. And so it's a very active, ongoing area of research. So we've talked a lot about foundation models, which are just large scale general purpose models that can be applied to all sorts of modalities and tasks. So obviously models such as the GPT series, which are foundation models for language, as well as many other types of models that can apply to other domains such as audio, images, videos, time series, and so on. And one thing in common with all these foundation models is that their architectures have largely been static, or they've been pretty established. And the part that does the heavy lifting is what I call a sequence model, which is for basically all current large foundation models is the self-attention layer. But more abstractly, the workhorse of all of these models is this primitive, this inner building block, which is the component of it that models the sequences. And so for any sort of modality that has the form of sequences, or even things that don't, such as images, you can still convert them into sequences, and the part of the model that does all the heavy lifting is this the part that mixes across the sequence dimension, which is what I call the sequence model. So so today I'm going to talk a lot about the this abstraction and introduce these new flavors of sequence models and talk a lot about the trade-offs of these different sequence models. So I'm going to use a simplified definition of a sequence model. This term is used pretty generally in deep learning at large, but I'll use a pretty narrow technical definition. So my definition of a sequence model is going to be simply a parameterized function that maps an input sequence to an output sequence. So this is a basic illustration where the input and output sequences are both one-dimensional. Okay, so we're going to treat a sequence model as this black box. There are some parameters of the model, but it's and those parameters define a function so that you, in this case, let's just think of one-dimensional sequences. You give it a 1D sequence of numbers, and then it spits out a 1D sequence of numbers. Now, why is this definition kind of what we need? This is all we need to think about, because when we're talking about deep learning, what we mostly care about is what functions does your model represent and how to compute the forward pass of that function. And then learning happens kind of automatically by backpropagation and so on. So we're just going to be trying to model an abstract function. And there are some parameters there, and different models have different parameters. And then all we're going to think about is the forward pass, and then we're going to assume that the model is learning stuff by backprop. But yeah, so this is a very, very simple technical definition. It's just a sequence-to-sequence map. Now, this simple interface is really the interface of all of the modern sequence models that we work with in our modern neural networks. So, so kind of more specifically, if you've ever coded one of these in any framework, the interface of such a model is generally something that accepts a tensor with three axes, such as the mini batch dimension. And then the most important one is the length axis. And then there's another separate model dimension or channel dimension. And then we're going to restrict the case where the model just gives you an output of the same shape. And now many different families of such sequence models exist that just satisfy the simple interface. Of course, nowadays attention is the de facto sequence model. Before attention, RNNs were very popular, and these are things that you've covered in this week, I believe. And you can, of course, have other forms of functions that operate along the sequence, such as simple convolutions, and also more exotic things such as ODE-based methods, which are also a little more recent. So the thing that all of these have in common is that although their mechanisms are all very different, they all satisfy this very simple sequence-to-sequence mapping interface. Now, I also like making a distinction between this core sequence modeling building block versus the entire neural network architecture. So I'll make the distinction where normally when I talk about sequence models, I'll talk about a very simple, usually a very simple transformation on sequences. And for example, a 1D convolution layer is just a very simple linear transformation on sequences. The self-attention function is again a pretty simple transformation on sequences that only takes a few lines of code. And I'll be talking about state space models or SSMs. And again, these are actually have a very simple definition, and it's just kind of I think of it as an inner building block that operates in sequences. And now there's lots of distinctions between architectures, but these are a bit secondary to the main inner sequence model. And for example, CNNs and transformers are really not that different in terms of their neural network architecture. They all consist of residual blocks with normalization layers like batch norm or layer norm, and with linear projections and so on. The exact order of these are going to differ between different architectures, but they all have the same ingredients, and those often I think are less important than the core mechanism, which is for a convolution for CNNs, attention for transformers, and SSMs for there's also a bit of an unfortunate overload in terms where people refer to the neural network as an SSM as well. If I want to make the distinction, I'll call a neural network a state space neural network, just like a CNN is a convolutional neural network. And these are neural networks that use an SSM as the inner building block. Okay, so we'll talk about a couple of an overview of several of these different variants of SSMs. More specifically, I call them structured state space models, which is a particular variant of these that have developed in the context of deep learning. And this is to distinguish them from older models that were heavily used in engineering statistics, which are also called state space models. And they have a bunch of similarities, but are also different in many subtle but important ways. The first one we'll talk about is S4, which is kind of the original model that was developed of this nature. And then we'll talk about a more recent version of these called the selective state space model. And that led to the Mamba architecture. Now, once again, Mamba is a neural network architecture, which was a recent development that has become increasingly popular. This really refers to the entire architecture, but it uses a core inner SSM. These are often conflated, and it doesn't really matter which one you call which, but just when thinking about these, it can be helpful to make the distinction. And what's so interesting about these structured state space models is that they are somehow broadly related to all of these broad families of other types of sequence models. So all of these types of sequence models look like very disjoint and very different, but they all have something in common with state space models. And so I like to think of state space models as this very fundamental type of model that underlies or has connections to all of these other types of models. So just to get on the same page, so I'm mostly going to be talking about this specific type of model or architecture, but just to keep something in mind, let's think of a task. And the thing we'll keep in mind is autoregressive modeling, which is currently the dominant paradigm for pre-training of foundation models. And so hopefully you've all kind of seen some version of this, but just as a refresher, basically autoregressive modeling is where you're trying to model the distribution of sequences. And here it's illustrated kind of audio waveforms. And you model these by modeling the problem of, given any prefix of the sequence, guess the value of the next element of the sequence. So you're basically factorizing the distribution using the chain rule into a bunch of next element prediction problems or next token prediction. Now, one thing that is useful to emphasize is that the generation process of these models looks pretty different than other things. And so this illustrates the generation process where you generate one token at a time and feed it back in. This is exactly how models like GPT work and so on, as you probably know. But what's important is that the training time actually just falls back under our simple black box abstraction of a sequence model. So at generation time, you're generating these things one token at a time. But at training time, you get all the data at once, and you can basically use something called teacher forcing, where you make every prediction at once. And to do this, you really only need to have a single sequence-to-sequence map. So hopefully you've seen this. Otherwise, just take my word for it. So basically, you just need to set up your data in the right way. And then at training time, all you need to do is try to model the function of the inputs to outputs. And do that by passing it through multiple layers of this simple sequence-to-sequence transformation. Okay, so now let's take a look at, so this is going to be the running example to keep in mind. And now let's take a look at some of the existing sequence models and their trade-offs. Okay, so you've seen RNNs, which are kind of a very natural model for sequential data, and this was kind of the most common type of sequence model before transformers became popular. So they're defined basically by here's a sequence-to-sequence map. Here it's illustrated. Your inputs are called X, the outputs are called H. And to compute this map, you basically pass in the inputs one element at a time. And the model is going to store some internal hidden state. And then you combine, what an RNN does is it just does a stateful update where it's going to always combine its hidden state with the input to produce the next hidden state, as well as producing the next output. So basically, it's a very natural sequential mechanism that maintains a constant size state and updates your inputs one at a time. And so they had they had strong inductive bias for many types of sequential modeling problems. And they're also a very natural causal model if there's a notion of like left to rightness. And they're also very fast at generation time because you kind of, no matter how much history you've seen, processing one new input is going to take a constant amount of time. No matter where in the sequence you are, when you see the next input, you apply the same function on your input and your state to produce the next state. So it's always basically a constant time. Now the downside is that because they're sequential, this actually leads them to be very inefficient on modern accelerators, such as GPUs and TPUs. So this is one thing that we also kind of touched on during the panel about the interplay between hardware and software. And there's also some modeling issues or optimization issues. For example, there's a famous vanishing gradients problem where because you're computing, you might be unrolling this function over many, many time steps. And then when you backprop through it, it becomes harder to optimize and your gradients might explode or vanish. And so kind of we can look at the trade-offs of this model as being characterized by its characterization is that it is the natural sequential model, and that defines its trade-offs, both positive and negative. Now, on the other side of the spectrum is attention or transformers, but more specifically attention. And here the pros and cons of this model are characterized by the fact that it's basically the dense interaction model. So what attention does is it takes your sequence and it will look at every single pair of interactions. And so this again characterizes its trade-offs. So on the positives, it has very strong performance because it's able to kind of skip over all the previous history and look at any particular thing in the past that it cares about. And so it's been ascribed positives such as having long-range dependencies. It's just also very good at many types of tasks that kind of require having fine-grained control over stuff in the past. Also, the way it's defined makes it very parallelizable on modern hardware, and it's basically when like a couple of giant matrix multiplications, which are exactly what GPUs and TPUs are designed for. The downside, of course, is that it's doing all of this work. It's doing a ton of computation in order to do every single one of these comparisons. And that leads it to, and that kind of is both why it's good, but also why it's bad. So this might be doing an excessive amount of computation. Many people talk about this quadratic bottleneck problem. And as you might want more and more history, for example, if you ever want to start dealing with like continual or lifelong learning, where you just want to always accumulate your history, this just becomes untenable to scale. Similarly, the quadratic time problem is a training time phenomenon. It's exactly equivalent to the fact that at inference time, meaning that when we generate tokens in an autoregressive fashion, so like your GPT model is trying to produce the next word, every single step is going to take linear time in the length of the sequence that you've seen so far. So these are the main drawbacks of attention, which is lack of efficiency. Okay, so we'll kind of try to build up to the selective state spaces, which the goal of these was to try to get the best of all worlds here. So they are both, they're quite efficient. They're unlike normal RNNs, they are parallelizable during training time, but they still have the benefits of RNNs such as fast inference. They scale linearly in the sequence length instead of quadratically. Their performance is very good, and even on models that domains that transformers are very good at, such as language modeling, they've so far showed a lot of promise and have been basically matching transformers with some caveats. But they were kind of the first non-transformer model that could achieve this sort of performance. And then these are the two main things you care about. And once you start having, if you can get both of these, then you can start doing, you can start addressing cooler capabilities, such as can you really get long context, such as fitting in million length sequences without suffering too much efficiency wise. So hopefully we'll get to seeing some applications of these at the end. Okay, so that's kind of just a quick overview of what I mean by sequence model and kind of an outline of what we'll talk about. And so now I'll talk about some of the details of these state space models. Let me grab this water. Okay. And by the way, we can save questions for the end, but if there's any clarification questions, I'm happy to take any quick ones while I'm talking. Okay, so let's get started and talk about the actual definition. Oh, is there a question here? Yeah.
Just really quickly, since you mentioned in the previous slide that yeah, you can use selective state spaces for language modeling with some caveats. I was just curious if you can elaborate a little bit more on the caveats that you had.
Yeah, so that will probably get pretty into the weeds of the exact trade-offs of these models, but basically, for language modeling, the metric that people have cared about most is basically perplexity, or kind of, the how well are you predicting your next token, which is the pre-training objective. And for the most part, that is correlated very well with downstream evaluations and other capabilities. But I think, especially with the advent of alternatives to transformers, people have started kind of realizing that the perplexity might be a little coarse-grained, and there might be actually more finer grained and nuanced trade-offs between these models. And so it seems like there's some capabilities that these are better than transformers, and some that they might not be, some that they're worse than transformers on like very specific types of tasks or capabilities. Yeah, so that's kind of the caveat, which is on like more nuanced downstream tasks. But in terms of like perplexity, which is still what most people care about, and just like kind of like overall average performance, they've been performing very well. So yeah.
Okay, thank you.
Okay. I'm gonna continue because I have a lot of stuff to get through. So we'll see how far we get. So first, I just wanted to sort of like define the actual state space model. And so I said that I view these as a very fundamental model. Versions of these have been around for decades, starting from the Kalman filter, which is still around today, but kind of It's actually so the interesting thing is that there's lots of versions of these that kind of share the same equations, but I've started viewing as actually being quite fundamentally different in some ways. So, but just in terms of the definition of the model, it's defined by just these two equations, where the first one is actually defining continuous time through a differential equation. And let me just quickly go and explain how to interpret these equations. Although before that, I'll just mention that the reason why I call these class of models structured state space models, and when we talk about SSMs, we actually are referring to this family of models, is because these are models that are specifically meant to be used in deep learning, and so we kind of interpret them in many ways a little bit differently than some of the classical models like Kalman filters. Now, in the context of deep learning, these models are have many nice properties and are broadly related to other families of deep learning models, as I previously mentioned. And so I'll briefly talk about some of their main properties of the original type of state space models, which include connections to the classical SSMs from controls and engineering, as well as connecting to deep learning models such as RNNs and CNNs. Okay, so just in terms of the definition, so remember that I'm defining a state space model as something that maps a sequence to a sequence, and here we're going to just focus on 1D sequences. And so they're parameterized by the input is going to be denoted by x always, and they're parameterized by the collection of parameters theta. In the case of SSMs, theta is basically the set of matrices A, B, C, and D that we just saw. And so we're only going to care about what does the forward pass or what does this function look like. Now, one particularity of these models that is not shared by other types of sequence models is that these are actually mapping functions to functions. So because they were defined using this differential equation and basically they operate in continuous time, that means that the input to this is actually, you can view it as a continuous function x, and then this is going to return to you a continuous function y. Now, how does this mapping exactly work? So let's step through it in a little more detail. So these are the two equations of the SSM. They overall, as a sequence to sequence or function to function map, you can view it as a function that takes in this input function x of t and spits out this output function y of t. Now, this mapping is performed in two steps through the two equations, where the first equation is basically going to map your input function x to a expanded hidden state, which I call h for hidden state. So this mapping is performed through this first equation, which is a simple linear differential equation. And it's controlled by these matrices A and B, which have the kind of the following shapes, where B is an n by 1 vector. N is what's called the state dimension, which is basically you're expanding your one-dimensional functions to a higher dimensional hidden state, which is a controllable parameter. You can think of it as something like on the order of 100. And so B is going to, this matrix blows up your input to a 100-dimensional feature, and then that feature gets processed by this simple linear differential equation governed by this transition matrix A, which is a square matrix that controls the dynamics of the system. And that's going to give you a unique solution H, which is going to, you can think of it as a higher level multidimensional function. So here it's illustrated the case where n equals 4, so you can kind of think of your one-dimensional function got blown up to a 4-dimensional function through this differential equation. And then the second equation simply takes your hidden state and maps it back out to a one-dimensional output function. And this is done through a pointwise projection. So no mixing through time here. It's just that every single time step t, you basically can take the dot product of your hidden state with some learnable parameter c, or you can think of it as taking a linear combination of your state, the components of your state, to produce your output function. And then often these are depicted with this this final term that kind of adds in skips. It's kind of like a skip connection that adds in the original input again. But this term is a little less important for the math behind working with these models. Yeah, so these are the two equations are actually quite simple, and they basically think of them as, again, a sequence to sequence map or a function to function map that goes through a latent state And this latent state is what gives the model its name, the state space model, and that's what kind of is going to control a lot of the properties of the model. Now, so in terms of some of the basic properties of the model, we already kind of talked about the first one, which is that unlike things like transformers and most RNNs and CNNs, instead of operating on discrete sequences, these models actually operate on continuous signals, or at least some versions of these models basically are more naturally a continuous model. And this kind of informs the strengths of the model as well. This original variant of SSMs is particularly good for working with continuous data, such as, say, audio signals, some types of time series, maybe things like video, and less good at working with discrete sequences such as language. So this is something that we'll see later is what Mamba addresses. But there's many, but for other types of data that's not language, this type of model works very well, and it can do other interesting capabilities such as dynamically adjusting to the resolution of your data without retraining and stuff like that. Okay, so now the next two properties are going to concern more about how to actually compute these models and how they relate to things like RNNs and CNNs. And so we define the model as a function. So I define that the sequence model is it's basically it's a mapping from a sequence to a sequence. I just gave the definition of what the function is, but not how to compute it. Now, how would we actually compute this model if we're given some input data? Well, one way to do it is basically by essentially unrolling the differential equation. So the differential equation basically tells you how does your state evolve through time. And you can basically convert this into a recurrence through what are called discretization techniques. But essentially, one way you can compute this is basically saying, okay, I have this input sequence. I want to compute my output sequence. And what I'll do is I'll kind of unbind the input sequence, and at every single time step, I'll feed in a new input x of t, and then I'll update my hidden state using this equation to compute the new vector, my new hidden state vector h of t. And then I'll use that new hidden state to project it back out to a new output. And so basically, you can compute the whole state space model by literally just like following the equations in the most naive way and simulating how to unroll the entire differential equation or the recurrence. Now, the reason that this is important is because when we're talking about autoregressive models, or in general, any sort of online learning, or incremental learning, where you see the input one step at a time, which is of course also true for autoregressive generation. This type of recurrence, just like with normal RNNs, is very efficient, and it's constant time per step. And so just to kind of illustrate why that is kind of matters from the perspective of from a functional perspective, let's say that we have this large input sequence, and you can think of this if you like thinking about language, you can think of this as like a text prompt. And now, given this prompt, let's say that we get one new word, and then we want to produce your next output, which is going to be the guess of the next word. Well, as a function, this guess of the next word is something that depends on your entire prompt or your entire input seen so far, right? So you can view this basically as a function that consumes a sequence and predicts one next word. And so naturally, you should expect the time it takes to compute this function to scale with the length of your context or the dimensionality of your input. And this is true for models such as transformers, of course, but this can be made much more efficient for recurrent models such as SSMs. And so here, no matter how long the context is, you can actually compute the next prompt in constant time. And yeah, this is so when you phrase it like this, it's not a trivial property, and it's because of the fact that the state of the SSM can be updated incrementally. And so that's kind of the second property of the SSMs, which is that they can be viewed as a special type of recurrence. You can even call them basically a certain type of RNN, and this has associated benefits such as fast autoregressive inference. And then let me just finally mention the brief connection to CNNs, although this is not really going to be relevant for later versions such as Mamba. But one issue with the RNN point of view is that this will still suffer from the same drawbacks as normal RNNs, which is that they're sequential and they're not very efficient or parallelizable on GPUs. And so in particular, during training time, during generation time, you only see the inputs one at a time. That was the previous animation. But during training time, you actually see all the inputs ahead of time. And so if you still do this sequential pass, it's extremely inefficient on hardware. And so we want to find a way to parallelize that. And another issue is that materializing the state of the model is actually very slow because although this is a 1D to 1D map, if you have to materialize this inner state, which is say 100 dimensions, then you're paying 100 times the memory and computation cost of what you should be paying in terms of your 1D to 1D sequence map. So these were reasons why these are some particular considerations of these models to deep learning that were not considerations for other variants of state space models such as in controls and so on. And so this is where kind of a lot of the technical work had to go into to figuring out how to use these models. Now the convolution point of view basically was a solution to the computational issues at first, where as a map from the input to the output, we could actually compute this in one go without materializing this intermediate state. And so that avoids that problem of materializing this 100x larger state. And the reason you can do this is because state space models are equivalent to convolutions, which are basically your vanilla type of convolution where you take a convolution kernel, illustrated in green here. Basically, you can take your SSM parameters A, B, C, and D and convert them into a convolution kernel and then compute the output from the map from X to Y just by convolving the input with a particular convolution kernel. And so this is basically exactly the same as a normal convolution, with the difference that the convolution kernel is very long. Now, we can compute this still pretty efficiently using known techniques, in particular using the fast Fourier transform, which are some classical techniques from signal processing. But in terms of high level how to think of them, you can really think of these models, at least this version of SSM, as being very similar to CNNs, except that instead of having a local convolution kernel, you can have an infinitely long convolution kernel. And so this is one thing that also gives them long range memory. But in terms of, and so this is kind of how they relate to CNNs, and the interesting thing is that they have the reason why we care about this is that during training time we can compute it using the convolutional point of view to get efficient parallelizable computation. That's pretty efficient on GPUs. Then at inference time you can convert the model kind of into the recurrent form. And so the nice thing is that we can kind of call these like two different dual modes of the model where there's multiple equivalent ways to compute it that have different benefits in different regimes. And of course, these models can be viewed as continuous time, and that kind of informs their trade-offs in terms of modeling capabilities. There's a lot more that you can do with this, and so I just want to briefly mention that there is a lot of how these were developed involved kind of a lot of theoretical considerations about how to encode long-range memory. And so the original motivation for a lot of this line of work was this question of, if you have a recurrent model, how can you use it to encode the history of your input and reconstruct it later? And so I was kind of interested in basically asking this question of how do you avoid the vanishing gradients problem? How do you try to memorize inputs and capture long-range dependencies for as long as possible? So there's some very nice theory here, but I won't go into all the details, but there's kind of a lot of connections here. Now, one couple quick things I wanted to mention before moving on to the selective state space models, or Mamba. The key distinction between these original SSMs and the Mamba type of SSM is that the model that I just introduced and this basic type of SSM is what's called a linear time invariant SSM, which means that these parameters A, B, C, and D basically they're constants. So you can see that they're independent of time. So at every single time step, we're using the same dynamics to update our hidden state and to produce the next output. Now, this has a lot of nice properties, and in fact, this is exactly why the model is equivalent to convolutions. And there's been a lot of downstream work on either the recurrent or the convolutional point of views that kind of have built off of these types of SSMs, but have mostly focused on this linear time invariant setting for the equivalence to convolutions. And why is that? Well, one reason, one other characterization of these models that makes them different from normal RNNs is the concept of state expansion, which I kind of I introduced it as saying that you have a one-dimensional input. So here's just another kind of another depiction of SSMs, just showing some different viewpoints to illustrate them. But you can the control theory way of looking at them is that you have this input, one-dimensional input X. You blow it up with this column vector B, and then you have this higher dimensional hidden state that undergoes a control loop using the controlled through the differential equation, and then you project it back out, right? Now, one reason why these models are different from normal RNNs is that the hidden state is much bigger than the input. So hopefully you've kind of seen things like LSTMs and the classical RNNs, and they're very different in the sense because the hidden state size is much smaller. The hidden state size will basically be the same size as the input, whereas for structured state space models, the hidden state size can be much larger. And so this both gives them much stronger modeling capabilities, but also has the computational issues, which is one of the big areas to, this is where the research had to go in to figure out how to compute them faster. And the whole point of the linear time invariance is that it makes these models equivalent to the convolution, which let us bypass materializing this hidden state. So I just wanted to mention these two concepts, so kind of the time invariance and state expansion, because these are concepts that will directly be related to the Mamba variant of state space models. Okay, so I have a couple of slides of kind of just like clarifying what is a state space model, but I've kind of already talked about it, so I'll kind of skip these. But basically, in the nutshell of these is that the term SSM is very overloaded, and so it's just kind of a warning that if you talk about SSMs with your friends with engineering degrees, they might have no idea what you're talking about, because every field kind of has a different version of what they call a state space model, because state space models are a very broad concept. It's anything with the state space. And there's many different types of these that exist in different fields. And so that's why one reason why, although in machine learning and deep learning, we still call these state space models because it's a nice, simple, catchy term. If I need to make the distinction, I call them structured state space models, which are the type of models that we have seen today. There are some particular technical reasons behind them, which is that the state transition dynamics have to be structured in a certain way. And so there's a lot of work that went into this that I won't go into the details, but there's a lot of literature on this. Okay, so let's stop there for the overview of the original type of structured state space models, or the S4 variant of them. And then let's kind of talk about the Mamba variant of these. Yeah, I normally would, okay, question?
So what's the initial conditions for the state space model?
Can you clarify?
So you have a continuous time dynamical system. I'm
Yeah.
wondering what the what's the word? Initial conditions of the system are.
Yeah, actually this is kind of exactly where the there's some different interpretations of structured state space models with classical state space models. These are questions that one would ask when talking about like controls and dynamical systems and stuff, but actually they're not really they're kind of like the framing of how we use these in deep learning is different. So so I guess just to try to explain that very quickly, typically when you talk about like differential equations, you're trying to model some process, and a differential equation is defined both by the let's see if I can find the equation, both by like the differential equation as well as some sort of boundary or initial condition, right, that uniquely characterizes it. Here well, I guess the brief answer to this is that you can choose any initial condition you want. we by default will assume the initial condition is a hidden state of all zeros. But the point that I was trying to make is that there's no real underlying physical process that you're modeling. All we're viewing these is as a sequence map. And so basically, we're just viewing this as a function that takes in an input and returns an output. And this function is defined by this, and you can add in an additional parameter, which is h of 0, or the initial state. In practice, we've never seen this make a difference, and we just set it to 0. But you can also basically like learn that state. But the point is that you're viewing this just as a parameterized map from the input to the output, and then you chain these together into a deep neural network, and you're just we're just viewing this as a very expressive transformation on sequences that can hopefully model whatever data distribution we want, and we'll learn it with backpropagation. But yeah, so there is no like ground truth initial state or anything. It's all just a parameter that you choose in terms of how do you want to parameterize your function. Yeah. Yeah, so I guess one reason why I'm presenting it like this is because this is the way that it was developed, and so it's kind of, I think, important motivation for these models. But other versions of these, you can directly start from the discrete point of view. I think the continuous version is kind of a little more detached from Mamba, but it's kind of I just kind of one thing I want to emphasize here is that I promised to talk about the connections between these models to all of the all these major concepts of other types of sequence models, and these include things like neuro ODEs. So kind of these three properties kind of cover a lot of the connections to other sequence models such as neuro ODEs, RNNs, CNNs, and then we'll go more into a pure discrete version, which is Mamba, which connects more to attention. But this is just kind of trying to show all the properties of these models, and also as motivation for kind of a historical motivation for how they developed, and yeah, just to provide all this context. Okay, I'm gonna move on just for time constraints. And I'm happy to stay a bit longer to answer any follow-up questions. Okay, so let's so we kind of talked about the continuous variant of SSMs or structured SSMs, and now we'll kind of talk more about you can think of these as a more discrete variant of these, or as a more attention-like variant. And this is the variant that's been much better for things such as language modeling. Now, I have a particular perspective on these models, which tries to understand them through the lens of their autoregressive state. So I claim high level that many different types of sequence models can in fact be understood by examining their autoregressive state. And they can kind of be characterized through what is stored in their state. Now, what do I mean by this? So first of all, we can kind of think of any autoregressive model actually as a type of state space model. And I use this in quotes because it's not what we call SSMs, but by the broad definition of state space model, any autoregressive model is a state space model because it stores a state, which is what it remembers in between time steps to process the next inputs. So let's look at some examples of this. So the definition of the state basically is that, say you're looking at your GPT model, in between generating every token, the model is going to have some memory that it's storing, and your state is just whatever that is. Okay, so let's revisit some of the models that we talked about, these baseline models. And we talked about RNNs and said that they were characterized by being a sequential model. And we talked about attention, which we said was characterized by being a model that looks at the dense interactions among the data. Now I'm going to revisit these and instead claim that RNNs and both of these can instead be characterized by what is their state. So let's look at the RNN first. What is the state of an RNN? Here the RNN is basically like defined through a hidden state, so it's very obvious. It's almost definitional what the state is, which is that an RNN always has a hidden state, which is basically a fixed size vector. Excuse me, and this vector is I drew it here because it basically represents what is the model storing in between time steps. And then, so it has this hidden, this fixed size state. You get a new input and you combine it with your state. Now, the characterization here is that this vector is a constant size. In other words, the model must be doing strong compression of its history. So say that the model has seen many inputs, like a long sequence. It still is maintaining a fixed size hidden state. And so that state is doing some sort of, it's trying to do some sort of compression of the entire history of what the model has seen. And this kind of informs its trade-offs. So first of all, we said that RNNs are very efficient and they're natural for modeling sequences, and they have fast inference time. And that's all because it has a fixed size hidden state, so that no matter how long your sequence is, you process one new input, you apply your same combination function, and this is always constant time. Now, this also says what are the downside of these models? Well, besides the fact that it is sequential, which is kind of a hardware constraint, this also explains why that these perform so much worse than transformers on language, because certain types of data, such as language, is very information dense, and trying to compress all of that information into a fixed size state is basically a hard or impossible problem. And so you just don't have the information capacity to model. And now we can again use this notion of a state to think about transformers as well. So here the definition of the state is just going to be a cache of the entire history of what the model has seen. So I'm not sure if you have all seen this or if it was covered earlier, but there's this concept called the KV cache of transformers, which is what's used at inference time. And what that means, basically, more higher level, basically, we saw attention is something that computes all pairs of interactions between every pair of position in your sequence. Now, what happens when you get one new input? Let's say this was your new input. How do you compute every single dense interaction? Well, to compute the interactions between your current input and every single past input, we must have stored those inputs, right? So because otherwise we would have lost access to them. So we must be literally caching every single past input that we've seen in order to compute our attention function properly. And so that's what the KV cache is. And basically, this is what we will define as the state of the model, because that is what the model is storing in memory in between processing the next input. And so because the state of this model is literally a cache of your entire history, this model is doing no compression. And so this is the opposite extreme of RNNs. And this again informs its trade-offs. We said that attention has very strong performance, especially on data such as language. And at training time, it's modeling all connections. But another way to think about it is that as a autoregressive model, it has a state that is storing everything, and so it basically has it's doing an expensive thing that has access to your entire history. But that's exactly also why it's inefficient. This is why processing a new input at inference time takes linear time, and that's the same reason why computing a forward pass of this model at training time takes quadratic time. And so you can think of the downside as that maybe caching your entire history is sort of wasteful. What if you have like irrelevant tokens or irrelevant inputs, or you just don't want to model things at the same resolution as the input you're given? For example, if you're doing character level language modeling, maybe that's kind of wasteful. Why do we want to cache one thing per character instead of per word? And so these are all the downsides of attention. And so this gives us a nice clean way to think about the trade-offs of these models. And so just to recap that one more time, attention is we can think of it as the de facto model that has no state compression. This gives it strong performance but poor efficiency. And state space models and other types of recurrent models in general have very strong state compression because they're compressing it to a fixed size state. And this gives them better efficiency but worse performance. And now this motivates kind of like what do we need to do to overcome the limitations of these models. So from a transformer point of view, as I just mentioned, caching the entire history is wasteful, and basically it's not going to be good unless one reason why they work so well for language is because your data has been processed so carefully for transformers and kind of tokenized carefully so that they work well. But in general, it's kind of wasteful to do this, and so compression really is important. You want to compress your data to only remember relevant information, or to compress them into higher level concepts that your model can work with. And from an SSM or recurrent point of view, what we need to make these models better is a more expressive state. And this involves two different axes. One is that we need our state to be a large enough size to remember what we need to. And this is kind of just an obvious kind of like information bottleneck. So this might depend on your data or your task, but whatever it is, the one characteristic of these stateful models is that once it's forgotten something, it can never get it back, right? So it needs to be large enough to store all the information it needs in order to perform the task at hand. And then also you want that state update function to be as expressive as possible, or as flexible in general as possible, so that it can store and process the information in its state however it needs to. Okay, and this is one reason again why SSMs compared to older RNNs are better, because they have this state expansion factor, which I emphasized, that gives them the ability to have larger states that can remember more information. And now the second thing that we need to address is how to make that state update function more expressive. And here the difference between the continuous type models that we saw and the selective stasis models is the only difference is that we're going to make the parameters a function of the input. And there are some very clear synthetic tasks that you can look at to understand why you need to do this. But for the sake of time, I'll just give a very high level overview, which is that let's look at this equation. And the first equation controls what is going into your hidden state, right? So this controls the evolution of your system, what is going into my hidden state, depending on my current input. And now the issue with this equation, or what's illustrated here is the linear time invariant SSM, which recall means that the ABCD parameters are constants. And the issue with that is that no matter what my input is, I'm going to kind of update my state in the same way. And this gives me very little control over what the state is learning. And so for a very simple example, suppose that I am feeding in a irrelevant input x of t. At my current time step, I'm going to give my model kind of a useless input. Then we really don't want to incorporate that into the state. On the other hand, if I'm giving it a very useful input, then I want to kind of incorporate more of that into the state, maybe even forget some more of what it was originally in the state. And so the point is that in order to get better performance on kind of like dense information data, we need finer grained control over these parameters. And so basically the only insight, it's a very simple change, is just that we will make the parameters A and B functions of the input. So instead of being constants, we're going to say that A itself is going to be a projection of the input x. That's going to give me my state transition matrix. And sorry, the fly's bothering me. And that's going to and that will make the model much more expressive, which will give me my more expressive state updates. Yeah, and that's really the only change in terms of like high level definition of the model. As I said, there's some very clear tasks, synthetic tasks that you can study to understand why this is clearly going to be better. I'll skip these for today. Let's talk about the one last component is that this was a very simple change, and when you think about the motivation, it's actually pretty obvious. And in fact, years ago, before we even came up with these structured SSMs, before we came up with the linear time invariant ones, I actually wanted to do this kind of selective variant. But the issue I kept running into was that we couldn't get it fast enough on GPU. And so this kind of touches on, the hardware lottery and these other things that we talked about earlier as well. But this is kind of the last bottleneck that's needed to make these models practical. And here, by the way, is just another kind of illustration or viewpoint of these models, where we are computing this map from X to Y through this larger hidden state H, an expanded state. And now the only insight that we the only last ingredient we need is now to do some very specific implementation, specific stuff that's tailored for our hardware. So this is an increasingly important area of machine learning as well, to how to make things efficient. But the very brief synopsis is that now, so previously we talked about state expansion is good because it gives you more expressiveness, but it's bad because materializing it will be too expensive. And previously we avoided it by using LTI models and by completely avoiding materializing the state by using this alternate computation entirely, the convolution. And now the issue is that we still can't materialize the state, even with selective SSMs. So we just need one trick, which is a very like implementation specific thing, which is that here we're going to kind of implicitly materialize the state because we need to in order to compute this time varying or selective SSM. But we're just going to be a lot more clever about where we're materializing the state. So now we're given this one-dimensional input x, we're actually still going to compute the entire, say, 100-dimensional state. But instead of computing it in main memory, which was illustrated in green in this figure, we're going to compute it in a more efficient level of the memory hierarchy, or SRAM, which is illustrated in orange here. So I'm not going to go into the details of all of this. How does this interact with hardware exactly? But just the high level takeaway is that when you move from the time invariant SSMs that we previously saw, like S4, and when we move to the time varying SSMs or selective SSMs like Mamba, we now do have to materialize the state. And now you have to be a lot more clever about how do you actually implement and compute these models. And there's a strong interplay with hardware as well. But that's kind of the implementation specific details. And yeah, the high level takeaway is all about the state representation. So if that's one thing that you remember kind of from how to think about sequence models, especially autoregressive sequence models, this is the thing. What goes into your state is the most important facet of your model. And different models appear on opposite sides of the spectrum, from basic SSMs do have a fixed size state and inflexible state transition, which gives them poor state compression, while models such as transformers or attention have no state compression, which also makes them more powerful but less efficient. And so the selection mechanism allows us to compress the data selectively, which is what we want to get the best of both worlds, and allows you to do context-dependent reasoning. And we have to pay attention to our implementation or other ways of defining the model to still be able to compute these efficiently, to get state expansion without the efficiency penalty. Okay, we're almost done. So I'll just talk about a little bit about some empirical results, and then I'll take questions at the end with any time left. So one thing that I like emphasizing is that I think there is no free lunch when it comes to modeling, at least with our current tools. And there's this kind of common perception that transformers can just be used everywhere. And they are very powerful in all sorts of modalities, but there is more subtlety to it. So on data that I call more discrete data, such as text, where there's the inputs are very discrete, and other things such as say DNA sequences are very discrete. I call this discrete data, and this is where attention shines and where Mamba also does well. But there's a spectrum of this where you can move to more continuous data, which are kind of more things that are sampled from underlying continuous signals, such as video, images, or audio. These are really like continuous, like audio is really a continuous waveform, and this is a completely different type of sequence data. And there's really no free lunch, and different types of models are better at different types of data. And the linear time invariant type of structured SSMs, in particular S4 and all of its follow-ups, as well as kind of like vanilla convolutional neural networks, really work better on continuous data. And this is something that people are kind of hiding when they say that transformers work well everywhere. Actually, they're probably using some sort of CNN to encode the raw data, or an SSM or something like that. And so S4 or the continuous version of structured SSMs are really good for this type of data, whereas the discrete or selective version of structured SSMs are much better at data such as text. And so I'll only kind of show the results for Mamba or the selective SSM because that's what got people really excited this year. And basically, I mentioned that I kind of matched transformers, and what we meant by that is kind of the standard scaling laws, which is what people use to measure how well does your model language and how well does it scale as you make the model bigger. And so with our, and this is also one way that on academic resources, you can still do meaningful work without needing to train large models because you show the scaling laws that usually will extrapolate to larger models. So this is using a regime called the chinchilla scaling laws. And we compared against on a couple of different sequence lengths. And what we saw is that especially for longer sequences, these models did better than a lot of these other types of baselines, which include kind of vanilla transformers, which kind of like the type of transformer that was seen in the original paper and was still used around when GPT-3 came out. That's here. And since then, there have been lots of other models that other types of SSMs basically, such as like the continuous or the continuous SSM. Many of these were proposed and many of them did better than basic transformers and claimed to be better than the standard transformer. But actually, when we ran a much stronger modern recipe, which we call the transformer plus plus, which is kind of a very modern recipe that most modern models use, such as Llama. Probably most of the large-scale models that you see these days that are released are based on some variant of this. And this scales better than all these other variants that people proposed. But Mamba was kind of the first to show that it was really seemed to be at least on perplexity scaled as well with a very strong modern transformer. Since this original plot, a lot more evaluation has come out, and basically it does still seem like this holds even at larger scales, but there are some caveats on like some very specific capabilities might benefit from having attention layers. And so actually right now, some of the best models that people are using are hybrid models that use some of both. And I'll just show one more last thing, which is that this is really meant to be a general purpose sequence model that works on all sorts of data. It's very flexible. It's just like a building block that goes into your neural network and you can apply it lots of places. We also investigated different types of data such as DNA, which you can kind of view as a different type of language modeling using a different alphabet of DNA base pairs. And here's an example where in this setting that has not really co-evolved with the transformer, when we applied these models out of the box, we found that Mamba was significantly better than transformers. So we did the same sort of scaling laws, including other DNA-specific models, as well as the same transformer plus plus baseline, and as well as Mamba. We use smaller models here, but you can still see the scaling laws. And there's a pretty significant gap in the performance here, where yeah, at the largest size, Mamba was matching the performance of the transformer with many fewer parameters. And I have a bunch of intuitions for why this might be true. I kind of mentioned one reason is like DNA is more fine-grained data, and so transformers just don't really make sense on the flop trade-off for you don't want to be caching, you know, like a something for every single token you've seen when you have such fine resolution data. But this is just an example where on other types of data, you can apply any of these models, and it seems to be just a general purpose, powerful, and flexible building block that can be used in a lot of places. And I also mentioned that you can scale these up to sequences of 1 million, and the performance seems to improve the longer the sequence gets. So it is because of its efficiency and its this selection that give it powerful performance. It actually is benefiting from longer and longer context. I have some more things, but I think I'll stop here. So we can kind of like measure the speed of these models and show that they are indeed very efficient and faster than attention, especially as the sequence length gets longer. And very recently, we released a follow-up to Mamba, which really connects this better to attention, and addresses a couple of issues with the original Mamba. But I'll just leave this as a teaser. We can talk about it another time, but let's stop here. And I can take questions as well.
Okay, I could start with one question. High level, how easy is it to train these models?
The question was, how easy is it to train?
Yeah,
By that, do you mean kind of computationally or like tuning
Optimization.
hyperparameters, stability, these things?
yeah, stability, hyperparameters.
Yeah, so there's always challenges training models, especially at larger scale and with newer things. Many techniques have been developed specifically for transformers to like stabilize them and so on. When we train these models, we didn't find any issues at the scales that we were training them on. And like, for example, when we apply them on DNA or other domains, they kind of mostly work out of the box. But I have heard that people who are scaling them to even larger have run into stability issues. And so there's room to develop more specific techniques to stabilize these models as well. Yeah, I mean, I know of a few of them, but they're kind of like you can apply a bunch of tricks or techniques to make them more stable. But there doesn't seem to be any like fundamental issue. And then in terms of like hyperparameters and so on, actually like generally whatever works for a transformer usually works pretty well here, but you can so it's not like super sensitive to tuning or anything. Usually, in my experience on a lot of the domains I've worked on and for example, what my company Cartesia has been training, it mostly works out of the box.
Thank you.
Question? Yeah.
So maybe more on the side of using this for time series forecasting. Have you done it, and what have you done? And like, what do you see in terms of performance? Then another question is, okay, X can be any, you showed one dimension, but can be any dimension, right?
Okay, yeah. So okay, so the first question is about time series. So in early versions of these works, we have tried to apply them to time series forecasting as well. We seem to find better performance, but actually I'm a little hesitant to say anything conclusive there because time series forecasting is a really tricky domain with like lots of other types of considerations. Like it really has issues with like overfitting and so on, out of domain generalization and so on. Whereas in language modeling, you pretty much never run out of data. And so they're just very different difficulties with these settings. And in the time series forecasting literature, people have been claiming that even like very simple linear models work as well. And it's very inconclusive in general. So I won't say anything definitive there. But I do think that depending on the type of data, I believe that these would be a very natural model to use because of like, just for example, depending on your time series, if they're sampled very fine-grained, then they're more continuous. I think that the continuous type of models would work well there. The other question was that I did mention that I used a very narrow definition of a sequence model, which is like a 1D to 1D sequence map. How do we deal with models with higher dimensions? Was that the question?
Yeah.
Or deal with data that have larger dimensions? This is a good question. And so the answer is just you can do something very dumb, which is that if you have like 1,000 dimensional data, you apply a sequence model on each dimension of or channel of this data independently, and then you mix across the channels using a separate module like an MLP or feed-forward network, or anything else can mix separately across the channels. So you can kind of view it as yeah, actually, this is actually a trick that was used before all of this in CNN land. Some of the most modern CNNs basically use this technique, which in that literature is called depthwise convolutions. And basically, it's the exact same idea where you take your sequence model or convolution only along each channel independently, and then you mix them using separate linear projections.
Okay, and maybe just another quick question, if
Yeah.
it's okay. So maybe I'm thinking on the LU. You're using LU1 to predict the next or generate the next second. And you train on an LU, and you got your model. And let's say now we introduce some perturbation or some noise. How does it affect in terms I don't know, it seems that you're trying to map a function, not sure if it's overfitting, and then when you put maybe a little bit of noise, it can or cannot generate good quality data. I don't know. If this makes sense.
I haven't investigated this myself. This is kind of a question more about sequence models in general. Like you can ask this about any sequence model, right? So it's your question about whether these are more robust or less robust to noise perturbations. This I don't really know. I again like I mostly think of these as just black box sequence transformation, and I guess this is why data matters and so on. So most people just don't think about this question. You assume your data is good. I don't know if they're particularly less or more sensitive than other types of models.
Thank you.
So a follow-up of your previous answer. So in the earlier models, S4 and I think the first Mamba, the strategy was to copy each SSM along the feature dimensions, right? It was in Mamba 2, I think you have like different SSMs for different feature dimensions.
That's right.
And another difference is so it looks like the state matrix, the matrix A in your slides, progressively became simpler and simpler, right? Do you have any comments about with all your experimentation, what kind of difference these two things make?
Yeah, sorry. We found that simplifying the dynamics generally hasn't seemed to hurt performance, at least empirically. And there may be kind of a conflation of multiple factors where maybe simpler models are less expressive but are easier to train using backpropagation or whatever, or using our non-convex optimization. It's not quite clear, but at least in practice, the simpler versions have always seemed to not really be worse. I do think that between Mamba and Mamba 2, which has a particular simplification of the model, I'm not quite sure if there could be a downside. There could be, and I just personally haven't experimented enough. So it's possible, but in practice, it's really been pretty reasonable. There are kind of theoretical results that show that there is supposed to be a separation of expressivity between the structure of your A matrix. So basically so kind of in theory, it seems like having more expressive A matrices can make your model like a step change in its expressiveness. For example, there's a recent paper called The Illusion of State in State-Space Models, where they basically say that if you simplify your A matrix too much, then it will suddenly lose the ability to model certain types of formal languages. But in practice, we've never seen this be an issue, and there's also and the simplifications also give you a lot of efficiency benefits. But it's unclear, yeah.
First, thank you for this nice presentation and congrats for our releases this week. So my question is more related with Hydra that was released, the new model that is like
Hydra, okay.
Hydra,
Yeah.
yeah. So I think that we're seeing in encoders or retriever models is like they use a causal language modeling and then they basically change to a bidirectional attention and do simple fine tuning. Can you do the same with Mamba, like transform to Hydra and do simple fine tuning to have like the bidirectional, but without having like the full pre-training of Hydra?
Yeah, I think that's kind of like a little bit orthogonal from the architecture. So basically all of those still apply, I think. Sorry, this fly is really bothering me. I think like it's possible there's differences in performance with different architectures, but I think we have done some stuff with fine tuning. Instead of training from scratch, you can fine tune models and generally kind of see the same sorts of lifts in performance or the same general patterns in what the models can do. There could be some differences on very specific types of downstream tasks. So one thing I mentioned in terms of like the nuances of the trade-offs of these models is that One example that people have liked to talk about is like a basic copying task. Actually, I kind of had some slides that I skipped here, where like if you just want to copy a bunch of inputs over, and if you want to copy like a lot of inputs, you can't really do this. This becomes less efficient with the state space model because you have a fixed size state. So this is kind of like a pathological example where, and so you might see some differences in certain types of fine tuning tasks, but in general, you can fine tune these models just fine and like use them the same way that you might change the setting of using a transformer as well. And same patterns usually hold.
Can I ask? Thank you for the talk. This is, I guess, a bit related to what you just answered, but what is your like experience in terms of like data efficiency with these models? Like, do you have any experience with like if they like have less data requirements or similar to
Yeah, so
current models?
that's a bit of a tricky question because if you really want to disentangle data efficiency from computational efficiency, you might want to talk about like we start talking about issues of like overfitting and inductive bias and stuff. And so it really depends on the domain and the tasks that you care about. So one kind of answer to this is that depending on your task, like there's kind of like some smaller scale benchmarks such as like one of the original ones that S4 became known for is long range arena and other sorts of maybe for time series and stuff where you're data limited. That's one aspect of measuring data efficiency. And if you choose your model appropriately, for example, use a continuous model for continuous data, you do see dramatic better trade-offs in terms of data efficiency. Another aspect would be like if you're just measuring, say, like language modeling by number of examples, you like number of examples seen rather than amount of computation done. And there, I think generally it's been pretty comparable. And it's not quite clear what the right measure is because these are regimes where there's mostly unlimited data and people normally care more about the compute efficiency. There's a prevailing viewpoint right now, which is that pre-training is basically how do you turn your like it's just a matter of flops. Like how many flops are you going to shove through your model, and that's how well that's how the model scales, how well it's learning, and that's what people think matters more than data efficiency in these settings. So this is a very nuanced question, but that kind of touches on a few of the facets.
Yeah, thank you. And can I just ask a quick follow-up or? Okay, then if someone else has like a better question.
Oh, there's one back there.
Hi, I enjoyed your talk, and I'll wrap this back to your panel discussion where you mentioned that you like to do things from first principles, and it sounds like there's a very large hack going on to make this work on GPUs. Are you revisiting the hardware question where you're using like analog paradigms versus digital paradigms?
Sorry. So in this case, I guess most of what I was concerned about with developing this line of work is the modeling question, and I think there's a lot of very nice fundamental theory that went into this to develop these models. Now, getting them to run on hardware efficiently is like, as I mentioned, entirely separate question, which is still something that you have to pay attention to in order to show that something works and to get adoption. And so you can view this as kind of a trick that to make it work on GPUs, and we've had to modify the models in ways to make them efficient on GPUs. I personally would love it if people got interested enough in these to start developing specific hardware for it. But as we kind of touched on earlier, it is very hard to break the hardware lottery cycle. But if you do something different enough, but a step change that can start encouraging this to change. And so people are kind of getting much more interested in these and potentially might consider baking in primitives of these into future generations of hardware. But I guess that's something I try to encourage, but it's not something I personally do or work on, right? But definitely it's something that I hope will continue happening. And it will be a slow process, but it is starting to happen.
Okay, let's thank the speaker again. And now, before you leave, we're going to make the closing of the school. It won't take long, and then we can all and drink some beers or anything.
Yes. I'm just.
Okay, guys. Is there something on the screen? Now?
It is.
Okay.
Okay.
Let's go. Okay, so I'm here in the name of all the speakers. You know, the ones they have been moving around. You know their names. We usually do this every year in the last minute, as you can guess. And I haven't seen these slides more than in diagonal, so I will basically try to improvise and see what happens. I hope it's good. And you don't get very bored. So usually we do this thing of looking where people come from. You can see this very large orange thing in the bottom. That's not a mistake. There's like a large diversity, and even though we get most of people from Portugal and some parts of Europe, there's people around the world here. We normally take pride on the proportions on diversity and stuff like this. I have to say, maybe this year we could have done a better work, but we definitely put a lot of effort in this type of things. Then if you look at a map, we have, as said, people from all around the world. And this is really good for us because I think that it takes some effort to come here, right? So it's great that we managed to cover so many places. In terms of kind of the feedback that we got a lot of feedback. So it's going to take a while to get over it. But let's see. In general, people are happy. I think people in general are always happy. There are always opinions about what to do with the labs, and we're definitely going to do a lot of stuff we have been doing, and we will keep changing. It's hard to have something that has everybody happy. I would say there's a large variance in background, and you will see this throughout of these feedback things. It's very hard to do one single thing for everybody. So you can think certain parts of the school might appeal more for some of you and others not, right? That's very hard to avoid. The question of the target of the school, who should we aim for comes every year. I think that we could definitely improve that. But as I said, it's a mix. If you look at the morning sessions and the afternoon sessions, there's clearly they're very different. Like the level that you see in the morning sessions sometimes is not sufficient to kind of enjoy some of the afternoon sessions. But again, this speaks also to the diversity in terms of backgrounds of people that come here, right? And hopefully you got something from different places. There's these birds of a feather sessions. That's something that we can definitely consider. Okay. In terms of happiness, everybody is generally happy. There's this yellow kind of nasty answer there. You can see it's not to be found in the cheese, in the, the bowl. And I mean, we judge this as good. Actually, Bruno removed the other thing. I guess I'm hoping all greens are good. But mostly the red and the blue are there and they're reasonable. So I'm taking this as everybody's mostly happy. And then there's some people with strange opinions. Yeah, I mean, we really need to be better at the slide things and kind of announcing things and keeping you on track. We have been changing the tools. This year we tried Discord. I don't know if you like it. We used to use Slack. We're getting old. We're losing sense of the technology that we have to use. I don't know, maybe TikTok. I have no idea. But we will try. We have no trouble starting these things, so we will try another thing. In general, monitors got very good feedback. Like most people were happy. One person was quite unhappy, and we read some specific feedback. We're always happy to talk about this. Maybe we can always find time. You can reach me or any of the organization. We're happy to get the feedback individually and be sure that everything is addressed, right? But I think in general, everything went great. We all had a fun time. I don't know if it's here, but I saw there's a bigger stats, right? And I think I saw the recovery sessions were liked in general. So people appreciate coming back to the topics and being able to discuss with the monitors. I think that worked pretty well. And if it's there, yeah, in general, the labs, polite, guided interactions like what do you do? You leave a person alone, looking at the computer, maybe the person is not even working in the labs. It gets a bit weird to go there and say, oh, Facebook. I think that in general, we prefer to be kind of pushing people a bit, but sometimes it's hard, right? And sometimes people just like to be left alone with their things. It's a bit of two sides. I think also students should move a bit and kind of also be proactive in that sense. Yeah, I mean, it's as we have been developing this through the years, right? People like, for example, Antonio, I don't know if he's here, but he always takes the time to write the equations and these things. And I think you get basically a private tutor for a while. So I think that definitely has a good effort. He also always takes people to kind of concerts. I hope you have not missed that. If not, you have to come back as a monitor and then do it. Yeah. Matching backgrounds, I'm guessing this is more about the type of background people have. Yeah, okay. This okay, I think there's a list of things that we can improve. We are about to kind of drop the whole GitHub thing. We have been seriously looking at like this kind of online notebooks that we can get since we get funding from Google. We will see. We have specific action plans. Some of the monitors have been proposing ideas. So that's definitely something that we're looking into. The labs more related to the lectures. I think that happens in general. The related to the lectures, we're missing one multimodal day, which we will be making next year. But in general, I have the impression they're relatively matching. Maybe the startup of the school, we should have pinged you with the installation. I know that many of you kind of went to install things the first day, and that probably took us a bit of time, right? But maybe next year we'll be a bit more proactive and we'll ping you 1 or 2 weeks before. Yeah, that's the variance thing again, right? Like if you look at Cho's DPO talk and what was in the morning, it's impossible to have everybody happy. It's always going to be variance, right? And because this is so diverse, it's always impossible that everything in the school will appeal to you. I think at some point we will get to the temperature thing. Coffee breaks, more water stands, more visit. Yeah. I mean, the coffee has been improving a lot. I think the queue speed for coffee was reasonable, right? Like it used to be like people would get desperate because the coffee would be slowly served. I think this year was reasonable. The always outside we tried. Like actually, Fernando was he was always like looking like at the air. We actually had them outside and moved them inside because we thought, okay, no, there's wind, we have to be inside. So you were very close to be outside a couple of times. It didn't happen, but that was our intent, right? We definitely like outside more. Lunch breaks, long queue. Yeah, we used to have more than one place to go. That's what they have, but everybody came on time, right? So that's good. Banquet. I mean, who doesn't like the banquet? It's really good, right? Yeah, we never like we don't do toasts or things like this. We should maybe or some sort of more social stuff, but everybody had a fine from what I saw, right? And it's definitely very well served. Vegan and vegetarian options, I think there has been large improvement in general in Lisbon in the last years. It used to be worse, much worse, right? And you used to be looked weird upon when you ask for things. But yes, definitely that can always improve. Yeah, the variance thing, right? Too hot, too cold. I can guarantee you, 4 years ago, it was too hot. Too hot 100%. It was really hot. Like we didn't have air conditioning in some of the rooms. So there was no kind of 50-50. It was 100% too hot. So now it's too hot, too cold. So low, mean, high variance. I buy this. I'm happy with this. No, I don't think we're going to get better than this. Not enough leg room. Yeah, really? Okay. I mean, I'm Spanish. I'm short. I'm sorry. Maybe I tend to sit in the front. Okay, dimming the lights puts people to sleep. If you're jet lag like me, for sure. Like I struggle a couple of times. Yeah. Wow, too crowded. You should see. Like no, definitely. This is not very crowded compared to other. No. It's definitely not very crowded this year. Topics. There's many topics. We talk also with speakers. We keep changing topics from time to time. So definitely, some of these things sound great. Agents is of course the fashionable thing. We did have reinforcement learning at some point, adapters, stuff like that. Yeah, definitely. We will keep rotating topics, that's for sure. Overall assessment, all good. Yeah, the food options guided. Opportunities for interacting with the speakers. We will scan to see if we have specific things, but it would be good to have suggestions on your side of how to improve this because that's definitely something that's useful. We normally hope the banquet to be an opportunity and kind of maybe the coffee breaks and things like this where you do have access to speakers. But we can think about how to improve this. The poster session also had some previous feedback on possible directions of improvement. So we basically finished with the suggestions. Yes, keep in mind that this is basically run thanks to money from our sponsors, right? Which we spend in grants for bringing people here and also bringing some of the monitors here. And without them, it would be impossible to do this. So if you want to thank our speakers, we very much appreciate it. Also, like not directly sponsors, but we all work for companies. We're kind of senior now, and these companies very nicely let us come here and do these things. So definitely, I'm really thankful to them for the time they allow me here. Then, of course, the speakers. We have amazing lineup every year, and every year we bring new people, and they add new things, and we're really, really privileged. Lisbon also helps because it's an amazing place to come, but I think we appreciate the fact that they come here, some for 13 years, right? Like Slav or Noah have been here for many years, and they're really, really amazing. So please thank our speakers. Of course, the monitors team deserves some praise. That's a good pose. Nice. I think it's the best pose of all years. And of course, you. Thank you. And yeah, I think we're done. Thank you very much. And keep enjoying Lisbon for the rest of the day. Bye-bye.